Well, today we're going to talk about factoring. I got to be honest with you, this is a major concept in Algebra 2. We're not going to be on this just today or just tomorrow, but for many days. But listen, the reason it's a major concept is because it is so useful as you keep advancing in mathematics. And you'll find out that factoring often, it allows us to keep going. It allows us to do new things. So what is it? What is factoring? Well, really it's changing an equation or an expression to multiplication. And when you change it, you get like a different form, but it's still equal to the original equation. It's just useful for some different applications. Here's a simple expression, x squared plus 5x plus 6. We call it a trinomial, but it's not multiplication. It's addition. If I factor it, if I turn it into, you might say where it came from, if I turn it into x plus 3 times x plus 2, well, now I have a multiplication problem. And we would say that it's factored. So it's still equal. It's still equal to the original equation, but it's in a different form. And as you're going to find out, again, it can be really useful. So what we want to do is we want to look at some of the basic factoring sort of strategies. And I'm going to be using sort of this foldable, if you're at home, grab your favorite colored piece of paper and fold it up to look like one of these. Or just take notes. But we're going to kind of have like 4 sections. And then we'll use the back of it tomorrow for another type of sort of factoring. So we're going to get all kinds of good stuff on here. Okay, maybe you even want to label the inside of this as factoring. Alright, well, let's begin in the first sort of corner here with what's called GCF or monomial factoring. Now, GCF or monomial factoring is when you take something, out of an expression or out of an equation. So here we have what appears to be some very different terms. We've got a 12x cubed, we've got a minus 27x squared. There's a common GCF to each of these numbers. There's like a greatest common factor. In other words, the highest number that divides into 12 and 27. Well, it turns out that there is only one number that divides into 12 and 27. It's the number 3. But we call that the GCF. At least it's the GCF of the numbers. Now, x cubed and x squared also have a greatest common factor. It turns out that it's the largest amount of x that is common to both of those. Now, the first one has 3 x's, or x to the third. The second one has 2 x's, or x squared. But in common, they both have an x squared. They both have x squared as their greatest common factor. Now the question remains, what's on the inside? And the answer is, you just got to pretend that you divided out a 3. And if I divide out a 3 from 12, I'm left with 4. Now if I divide an x squared out of an x cubed, it's kind of like I took 2 of them away, but I'm still left with 1. Same thing with 27. If I divide the 3 out, well, I'm left with 9. The x squared, well, all of that got pulled out, so there's no x left. It'd be kind of silly to put an x there. I took all the x out. Now, one way to think of GCF factoring is to realize that you just undid the distributive property. That is, if you would do the distributive property, you should go back to where you started. And certainly we do. That's because we factored this correctly. But normally we don't go back because we wanted to change the problem. We wanted to change it into its factored form. Now, we will do another example in that corner later in the lesson. Let's move on to the next corner. Most people put this in the upper right corner where we have trinomial. Now, a trinomial is a pretty popular type of expression, and so we want to be pretty good at factoring it. And when you have a trinomial, one thing to realize is that it's always going to factor into two binomials. Now, these two binomials aren't just like a guess or a surprise where they come from. They come from kind of splitting up our x squared, our 9x and 20. And specifically, the x squared is definitely going to come from x and x. Now, the cool thing about the 20 and the 9 is that you can sort of solve a little puzzle. The little puzzle is two numbers that multiply to be 20, but add to be 9. What are we talking about? Well, numbers that multiply to be 20 would be numbers like 10 and 2. But do they add to be 9? No. How about 5 and 4? Oh, yeah, 5 and 4 multiply to be 20, and they also add to be 9. So that's the rest of our factors. So we have x plus 5, x plus 4. Now, I'm not going to show this every time, but you can always check your answer by distributing, or in this case, by doing like a FOIL method. And if you do the FOIL method, you're going to end up with where you started. That's because we factored this problem correctly. But again, we don't want to turn it back into the original problem. We want it to be factored. So we have x plus 5, x plus 4. Now, by the way, you could have written those in any order. In other words, you could have written the plus 4 first and the plus 5 second. Let's look at another expression. It's another trinomial. Nice thing about trinomials is that they always factor into two binomials. And these two binomials basically produce my x squared. So it's got to be x and x. Now, does the little puzzle work? Well, it sure does. You want numbers that multiply to be negative 12, but add to be negative 1. Now, numbers that multiply to be negative 12 and add to be negative 1 get a little trickier because we've got negatives involved. But what I usually encourage kids to do is don't worry about the negatives for a moment. Just think about numbers that multiply to be 12. How about 2 and 6? Now, is there any way to make a 2 and a 6 add to be negative 1? I don't think so. How about 4 and 3? Is there any way, those multiply to be 12, but is there any way to make those add to be a negative 1? That's right, if the 4 is negative, but the 3 is positive. So we have our factors, x minus 4, x plus 3. Let's do one more. How about x squared plus 26x plus 48? Now, yeah, when the numbers get bigger, we have to kind of know our times tables a little bit better. Remember, you want to start with numbers that multiply to be 48. So, again, how's that list? Sometimes people start with ones that they're familiar with, like 8 and 6. But they don't add to be 26. How about, is there a 16 that works with 48, I believe? Yeah, 16 and 3. They don't add to be 26. What's that you say? 24 and 2. Yeah, 24 and 2 multiply to be 48. And come to think of it, they add to be 26. So we have our factors. Now, factoring is really turning a problem into multiplication. And sometimes we just kind of have to think backwards using, in this case, like a little puzzle. But what if it's not just a trinomial, but it's a trinomial? Okay, now I kind of made this up, but basically a trinomial is a equation or expression, well, that has a coefficient. Now, as soon as you get a coefficient involved, you have to, well, think a little bit more. You have to adjust your little puzzle. Let's talk about it. So clearly we have a coefficient, that 3 on the x squared. That's what makes this problem more like a trinomial. Okay, so we've got this 3, and we're going to be working out on the x squared. Let's see. Instead of using x and x, I'm going to need 3x and x. Okay, that's important that you realize that we need a 3x and an x in order to achieve the 3x squared. Now, I still think about numbers that multiply to be 8. I still think about numbers that multiply to be 8. But they're not going to add to be negative 14. You're going to have to understand that they're going to check to be negative 14. Okay, how do they check? Well, let me show you. First of all, we need numbers that multiply to be 8. Okay, now that could be 8 and 1, and that could be 4 and 2. Okay, let's just kind of start with the 4 and the 2. Now, if you say, all right, so does that mean I can put a 4 and a 2 in here? Well, I don't know, does it? You see, I have to make sure that if I check the answer, that is if I take the 3x and distribute it to the 2, and I take the 4 and distribute it to the x. Now, a little by the way, that looks kind of like a forehead and a smiley face, or maybe just in general a smiley face. You see, when you're using this method though, you have to realize that when you multiply or distribute the 3x to the 2, you get a 6x. And when you multiply or distribute the 4 to the x, you get a 4x. What's up with this 6x and 4x? Well, they have to check to give you the negative 14x. I know it's negative, but is there any way for a 4 and a 6, that is a 4x and a 6x, is there any way to make them become a 14? No, there's not. So, does that mean I'm wrong when I use a 4 and a 2? Well, actually, it might just mean that I need to use a 2 and a 4. I might need to kind of do it the other way. Now, as you get faster at this, you'll be able to start to see how this works, maybe without doing all the guessing. But I'm going to distribute 3x to 4. That gives me a 12x. I'm going to distribute the 2 to the x, and that gives me a 2x. Now, is there any way to make a 12x and a 2x become a negative 14x? Well, there sure is. I just need both of them to be negative. And if both of them are negative, then of course my 12x is negative, and so is my 2x. We just factored that problem. We factored it by correctly choosing a minus 4 and a minus 2. Of course, in the opposite order that I just said it. So it's 3x minus 2 and it's x minus 4. Trinomial. It's got a coefficient. Whenever you have a coefficient, you have to be prepared to do a little bit more thinking. Now, first thing you got to think about is that it's got to be a 2x and an x. That's the only way to get a 2x squared. Now, the good news here is the only numbers that multiply to be 3 are 3 and 1. Remember, multiply to be this number. But they need to check to be this number. Now, if you put the 3 out here and the 1 right here, can you already see that that's not going to check? That's because I'm going to get 6x out of this and 1x out of this. Well, guys, 6x and 1x, I can't make those become a 5x. And I can't subtract them because, well, nothing's going to be negative. So, if you put the 2x to the 1 and the 3 to the x, do you see what you're going to get? Do you see what you're going to get when you kind of do the smiley face? You get a 2x, you get a 3x, and those check to be 5x. They check to be 5x when you make both of them positive. Okay, so a trinomial. We have to kind of think backwards. Okay, now, we're going to keep working with that. But for now, I'd like to show you one last situation. It's a little bit of an application of this factoring. It's called a rational. And you might want to put this in like the lower right corner. A rational expression, well, that's actually kind of a fancy way just to say an expression that is a fraction. Now, fractions obviously can be a little bit more complicated. Okay, but what we want to realize here is that the only way that I can simplify these fractions is if they are in factored form, Factored form means that they're being multiplied. So we want to think about how we can factor. For example, how can we factor the numerator? Okay, when you look at that expression, you want to say GCF. Say it with me, GCF. What's the highest number that divides into 6 and 18? Okay, that's definitely 6. And how many x's can I pull out? Okay, I can pull out the greatest amount that's common. That would be the x squared. Now, what's left over? What's left over when I take a 6 off of 6 is just the number 1. And when I take x squared off of x cubed, I'm still left with just x. When you take 6 off of 18, you're left with 3. That's because you divided it off. And the x squared, you might say, completely got factored out. Now, this guy down here, I know it's got 3 terms, but it's not really like a trinomial in the sense that we can factor it smoothly. But there is GCF written all over this. If you look at 3, 18, and 27, you could say that there's a common 3 that I could pull out. And then if you look at the x's, the most amount that's common would be the x squared. Okay, now sometimes kids will notice that it's like I'm just taking out the smallest x, but that's true because the smallest x is the greatest x that's common to all 3 of these. Okay, so we're good when we take out 3x squared. What's left? When you take 3 off of 3, you're just left with 1. When you take x squared off of x to the 4th, it reduces down to x squared. 18 got divided, so now it's down to 6. X squared got pulled off, I'm down to just x. 6x to be exact. And then over here, 9. What's going on here? Well, we're changing the problem to what's called factored form. Factored form is when things are multiplied. There's a multiplication sign right here, and you're going to find out in a second that that's good. Now, the other thing that I notice, or at least that I want you to notice, is that this part in green, well, it's a trinomial. Trinomials can be factored. They typically can factor into 2 binomials. Now remember, when you factor, you just want to look at the numbers and find numbers that multiply to be 9, but add to be 6. Am I allowed to just kind of do it the easy way? Yeah, because there's no coefficient. So what numbers multiply to be 9, but add to be 6? You got it. X plus 3, x plus 3. Now, if you look at this rational expression, it's the same as what I started with, but it's in factored form. Factored form means that things are being multiplied. And the rules of algebra would say that when I now have common factors, like this x plus 3 and this x plus 3, they can divide off. They can cancel out. So both of them are gone. How about this 6 and 3? They can divide or reduce like they always would to just be now 2, because it's like 6 divided by 3 is 2. And finally, these x squareds, well, they're completely the same. I'm allowed to cancel them. Look what I'm left with. Look what I'm only left with. Yeah, that is a much simpler expression, and it's equal to what I started with. Okay, I've just changed it to factored form so I could kind of divide out all the extra slack in that problem. That's the only rational one that we're going to do. I would like to go back to your foldable and add another example to this upper left corner that we'll sort of call like a combo problem. It's a combo problem similar to what you just saw, where we kind of use like multiple types of factoring. What do I mean, like multiple types of factoring? Well, again, here we have an expression that you honestly want to just look at and be able to deduce that there's a greatest common factor that you can take out of those numbers. It would be the number 2. And if you look at the x's, you would say that there's a certain amount of x that's common to those. Now, it would only be x, but what I've done is I've done like a GCF factoring. At least I started with GCF. Now, after you start with GCF factoring, maybe you can finish the problem with more like a trinomial factoring. Do you feel like that x squared plus 4x plus 3 fits nicely into the little puzzle where you use an x and an x, and then you look for numbers that multiply to be 3 but add to be 4. Now remember, the only numbers that multiply to be 3 are 3 and 1. And so now I have factored, or you might say I've continued to factor. And I end up with 3 factors, a 2x, an x plus 3, and an x plus 1. That used like a combination of factoring. Again, I used like GCF factoring, and then I also used like trinomial factoring. Okay, now for tonight, we're actually, in class here, there's some problems. If you click on the next paper that the kids are going to try, I encourage you to try those problems. You can just do them in a separate sheet of paper if you cannot print the paper, and then you'll notice on the back of that paper is where the homework is located. So take a look at that practice, then homework paper as your next step in this first factoring lesson.